In this lesson, I'll give an introduction to linear regression using SAS. So the objectives are, first of all, how to understand and use appropriate SAS procedures in the context of linear regression, and we'll talk about proc reg and proc GLM. You should understand how to interpret regression coefficients derived from these linear regression outputs. And we also want to interpret the intercept term derived from linear regression. We'll go over indicator variables, also known as dummy variables, how to code them in a data step, and then how to apply them within the context of a linear regression. And I'll also go over some useful examples of how to model categorical variables without the use of dummy coding. And then I'll quickly show an example of proc plot to create scatter plots, which can often be useful in the context of linear regression. Just a reminder, this is an example of the basic linear regression equation that we're estimating in these procedures. So we'll be modeling the mean of some outcome variable y, and that's going to be predicted by an intercept term, beta naught, plus a regression coefficient, beta 1, which will tell us the degree to which the outcome variable changes for every 1 unit increase in our independent variable x. And we'll discuss how to interpret these beta 1s and beta naughts based on the output that SAS provides. We'll start with proc reg, which has many different functions in addition to basic linear regression. One of the nice things about proc reg is that it can also provide you with some nice diagnostic statistics and plots fairly easily. We won't talk about those in this lesson, but it's one of the reasons why it's valuable to think about proc reg and understand how to use it. I highly recommend that you take a little bit of time to go over the SAS user guide and read up on proc reg so that you can see all the many different options and capabilities of proc reg beyond what we're going to talk about in this particular lesson. This is a quick and basic, very functional example of how proc reg could work. So I'm going to run this procedure in the context of our ongoing teaching examples regarding the relationship between various measures of body mass and body composition in relationship to systolic blood pressure. And we're using the reg procedure. So again, we start with the proc statement and specify that we're going to use the reg procedure specifically. And then we identify our data set, ending with the semicolon. And one of the most important statements that you'll use within the context of proc reg is the model statement. The model statement is simply where you specify the regression model that you want SAS to estimate, and the form of that is simply your dependent variable set equal to your independent variable or variables. Or in other words, generally speaking, y equals x, and in the specific context of our example, we want to regress the systolic blood pressure variable, SBP, across levels of the BMI variable. And the variable name for BMI is simply BMI. And we end with a semicolon and a run statement, and our semicolon. So why don't you try and run that now in your editor file, and then we'll jump over to the editor file and I'll run that and we can look briefly at the output. Now we'll go ahead and run this together in the editor file, and as usual I'm just going to start out in an editor file that I already have opened up, and I'm going to go through and set up a lib name, set up some formats that might be helpful, and then I'm going to actually set up the data set by merging together 4 starting data sets. And all of this is code that we've talked about previously throughout this course to help get our data operationalized appropriately for the analyses that we want to run. No errors there. And in SAS, in the editor file, here's the proc reg. You notice I added a quit statement. These quit statements simply are used in the context of some SAS procedures which are interactive, which simply means that if I only run down to the run statement, I will get output, but SAS holds some of the results from this regression in its internal memory in case I want to come back and ask for more models, for example. But it's generally good practice to include the quit statement so that SAS sort of deletes that internal memory and makes it available for faster processing. We'll highlight that, submit it. It brings us to the output window, and this is the basic form of the output within proc reg. So we have 12,724 observations that were read in and used because all of the observations had data for independent and dependent variables. By default, you get an ANOVA table for this regression and a couple of other helpful descriptive statistics. I've explained those and given some brief definitions in the slides of what this default output is talking about. Of most interest, I think, usually is the R-square, which simply tells you the proportion of the variation in your outcome variable that's explained by the independent variable. So that's a nice statistic to give you some information about how well the overall model does in terms of explaining your outcome variable. And the new information here in regard to linear regression is summarized at the end under the title Parameter Estimates. So here is our independent variable BMI. And then over here we have a parameter estimate for the independent variable BMI. So this is our beta 1. This is the slope of the regression line telling us how much systolic blood pressure changes on average for every 1 unit increase in BMI. Or in other words, for every 1.5 unit increase in BMI, systolic blood pressure increases on average by 1.5 millimeters of mercury. We have the standard error for that regression coefficient. There's a t-value that's calculated and a corresponding p-value that can be used to make inference and decide whether or not you believe this parameter estimate is different than 0, or in other words, is there evidence that there is some sort of linear relationship between BMI and systolic blood pressure. And there are 95% confidence intervals included in this output. And those 95% confidence intervals were generated by including the CLB option. That simply is an option that requests confidence bounds. Go back to the output. You'll also notice that there is a row corresponding to the intercept. So this is the parameter estimate for the intercept. Again, you also have standard error, t-values, p-values, and confidence intervals. And in the context of linear regression, the intercept simply refers to the mean value of your outcome when the independent variable is set to 0. So this is a basic y-intercept for a straight line equation. And in this particular context, when we're modeling BMI as the independent variable, the intercept does not have a lot of meaning because, of course, BMI of 0 is not a valid or plausible value. So you would only use this intercept if you wanted to calculate the actual predicted value of systolic blood pressure based on this model for a particular BMI. And you would do that by filling out the straight line equation. If we wanted to know, for example, the predicted BMI systolic blood pressure of an individual with a BMI of 20, we would take 93 plus 1.5 times 20, and that would give us the predicted BMI, the predicted systolic blood pressure of an individual with a BMI of 20 by combining information from the intercept term and the regression coefficient. And if you're interested in running multivariable models and adjusting for other variables, you simply add additional independent variables on the right-hand side of the equal sign. So here is a crude model of BMI predicting systolic blood pressure, and then here in line 186 we have a model that looks at the relationship between BMI and systolic blood pressure adjusted for age. Submit that. The output is very similar, but now we have a regression coefficient for age. For every 1 year increase in age, there's a 0.69 millimeter of mercury increase in systolic blood pressure. And again, you have standard errors, t-values, p-values, and confidence intervals. And now the BMI parameter estimate, or the regression coefficient, is now adjusted for age. In other words, we could say that after adjustment for age, every 1 unit increase in BMI is associated with a 1.15 millimeter of mercury increase in systolic blood pressure. And if you wanted to model additional variables, independent variables in this model, you would simply continue adding them to the right of the equal sign. As a reminder, the null hypothesis of the regression coefficient within the context of linear regression is that there's no linear association between the independent and the dependent variable, or in other words, the best line through the data. If you were to think about a scatter plot representing your data and drawing a line through it, that best line would be just a flat or horizontal line. And if you see evidence to reject the null hypothesis, then you're rejecting the null hypothesis in favor of the alternative, which is that there is, or does appear to be, some linear component of the relationship between your independent and dependent variables. When you're interpreting the regression coefficients and making these decisions about statistical significance, remember you would use the t-value and the p-value that corresponds to the actual regression coefficient of interest. So as we saw a moment ago in the output, for the BMI variable, you simply look across that row for BMI and you get information on not only the regression coefficient and the standard error, but you also get information regarding the t-value and the p-value corresponding to that regression coefficient. We also noted what the meaning of the intercept was. This, again, is simply the mean value of the dependent variable when the independent variable is set to 0. And in many situations, the intercept is not always very meaningful. Let's talk about some situations where the intercept could have some meaning, and at the same time demonstrate that dichotomous independent variables can be modeled within the context of linear regression. So when I'm talking about a dichotomous variable, I'm simply referring to some two-level categorical variable. We'll start with the example of gender in this data set. And you should think about how the intercept could be interpreted differently if we assign values of 1 and 2 to our gender variable. So in this example, we have a variable named sex, and it will take on values 1 of 2 in our initial regressions, and those values correspond to men and women. Now, the interpretation of the intercept is going to be different in that context as compared to a setting where maybe we define the sex variable to have values of 0 and 1. So at this point, why don't you try running a linear regression, modeling systolic blood pressure being equal to sex, and take a look at the output, and then we'll go through it together and interpret that. Okay. So here's our editor file. Now I'm just going to run a quick proc freak so we can look at the distribution of the sex variable and also see very explicitly what the values are. So the variable sex in this data set has values of 1 and 2. These are men and women respectively, and in this particular data set, about 62% of the participants are female. Now if we run our linear regression, we're having again, a model statement that is specifying SPP equal to sex. We submit that. We'll jump right down to our parameter estimates. So in this context, the intercept term, again, is reflecting the mean value of systolic blood pressure when the values of sex are equal to 0. But in this particular regression, since there are no situations, there are no observations in our data set who have a value of sex equal to 0, it's meaningless. And that's because we had arbitrarily defined the values of sex to be 1 and 2 in this particular data set. So we've run a regression where the intercept does not have a lot of meaning. However, the regression coefficient for the sex variable still has meaning. It's telling us what the change in mean blood pressure is when we compare men to women, or a 1-unit increase in the sex variable. And in this context, the 1-unit increase is comparing men versus women and calculating that the difference in the mean values. So this is telling us that when you compare mean systolic blood pressure among men and women, it goes down because a 1-unit increase is going from 1 to 2 in the context of values for this sex variable, and that then translates back to comparing men to women. So that's telling us that women have on average about 5.5 millimeters of mercury lower systolic blood pressure on average, and that's highly statistically significant. Our confidence intervals exclude 0. So we could reject the null hypothesis that mean systolic blood pressure is equal across levels of sex, and conclude that systolic blood pressure appears to be lower in women in this crude model. So now let's try and run that regression again using a different variable for sex, but this time changing the values of the new variable that we'll create. So if we come down here to this data step, I'm going to create a new temporary SAS data set named master1. It's temporary because it's in the work data library, and I'm starting from the data set, the SAS data set master, which we created previously in this lesson. And I'm going to create a new variable named sex2, which will take on values of 1 whenever the original or existing variable sex equals 1, and sex2 will take on values of 0 whenever the original variable sex equals 2. Now, in other words, this new variable sex2 will have values of 1 and 0. 1 corresponds to males, and 0 corresponds to females. Now, after we do this, it should become immediately apparent that the y-intercept will now have meaning. The y-intercept in this example will correspond to mean systolic blood pressure among females. Submit that, and then come down to our proc reg, where we're again modeling the relationship between SPP and this new variable sex2. And in this output, there are two key changes. First, the y-intercept is now different. The y-intercept here is corresponding to mean systolic blood pressure when sex2 equals 0, and those observations are the females. So mean systolic blood pressure among females is 130. The other thing that's changed very slightly is the regression coefficient. So again, this is now telling us for every 1 unit increase in the variable sex2, what is the change in mean systolic blood pressure. And since we changed the ordering of the variable, in other words, now females have a lower value than males. Females have a value of 0, and males have a value of 1 for the variable sex2. Whereas previously, females had a higher value. They had a value of 2 for the variable sex, and men had a value of 1 for the variable sex. So what that does is it simply changes the regression coefficient, because now we're looking at the change in blood pressure when you go from being female to male, or in other words, from having a value of 0 to a value of 1. but the absolute value of the regression coefficient is identical because, again, it simply represents the difference in the mean systolic blood pressure between men and women. The t-value and the p-value is identical as well. And so here you can see we went through a very quick example of how you can code your dichotomous variables that you might plan to use as independent variables in a regression in a way that would allow the intercept to have some meaning if you find that to be valuable, to have intercepts that have meaning. And the best way to do that, again, is to make sure that some level of the dichotomous variable is equal to 0. So I've just summarized what we just did in the slides, so you have that information available to you in the slides. And if you wanted, you could calculate the predicted value of systolic blood pressure for men and women based on the results of both models. So if you just took the results from our regression equation from the sex2 variable and plugged it in, you can calculate that the mean value of systolic blood pressure among women is about 131, and the mean value among men is 136, using this formula. And you could think of it graphically in this nature. So here are the females and here are the males. This is simply plotting their mean systolic blood pressures that we derived from the regression equation. And if you connect those lines and calculate the slope, that's the regression coefficient. So this is just a reminder for those of you who are very new to linear regression and trying to think about what regression coefficients correspond to in the context of these dichotomous variables. And this is simply an example of calculating the mean systolic blood pressure among men and women if you use the original regression, or that is, using the original sex variable. And you'll see that the mean blood pressures are identical. The values that you're inputting in the equation are slightly different, but you get the exact same result. Let's move on now and talk about a slightly more complicated situation in the context of linear regression, and that is when we want to model a nominal categorical variable as an independent variable in the context of linear regression. We'll think about the independent variable region, again predicting systolic blood pressure, and if you wanted to run a very basic and quick regression in proc reg, you could set that up as we have in other examples using proc reg, and your model statement would now say SPP equals region. So if we go over into SAS and run that, this would be the result. And at this point, let's just quickly look again at the parameter estimates. So what this is telling us is for every 1 unit increase in the region variable, and the region variable takes on values 1, 2, 3, and 4, there's a 0.4 unit increase, or millimeter of mercury increase in systolic blood pressure. And you could interpret the intercept as the mean systolic blood pressure among participants who have a value of 0 for region. But nobody in this data set has a value of 0, so this does not have a lot of meaning. And this linear regression coefficient is not terribly meaningful either, because it doesn't necessarily make sense to think that these arbitrary values of 1, 2, 3, and 4 that have been assigned to different regions of the country would be related in any sort of linear and constant fashion to the systolic blood pressure outcome. But SAS has no awareness of that, of course, and if you ask it to run that regression, it will go ahead and do it and give you this result. So there's your regression coefficient, a t-value, and then you see marginally statistically significant p-value. So effectively what's happening is we have a data set with values 1, 2, 3, and 4 for region. We ran a linear regression, These are the predicted mean values for each level of region in the data set, and this is the regression line. So based on the principles and the rules for linear regression, the program and algorithm is going to try and identify the best straight line through all of the data points, and this is the best straight line for the data structured in this nature. And this is simply the regression line that we saw from the SAS output a moment ago. Now, if we were to think about the results based on either a proc ANOVA or even a very simple proc means, which simply would tell us what is mean systolic blood pressure in the different regions, this is the pattern we see. These are mean systolic blood pressures in the Northeast, Midwest, South, and the West in this data set, unadjusted for any other variables in the data set. So clearly, the relationship is not linear. It looks like blood pressures really don't vary much in the Northeast, Midwest, and the West, but they are a bit higher in the South, and this difference could be meaningful. So we need to figure out a better way to model this relationship within the context of a linear regression. Because a basic linear model is causing us to lose some valuable information about the relationship between region and blood pressure. One common way to do this is to create indicator variables, or another name is dummy variables. And what these indicator variables are breaking some nominal variable with multiple levels down into a set of many different dichotomous independent variables that could be modeled in your regression. So doing this can be very useful when you have independent variables such as region that are nominal in nature. And in other words, the values assigned to the levels of the variable are arbitrary, and there's no real a priori belief or hypothesis that there should be a strict linear relationship between levels of that nominal variable and your outcome variable. To create indicator variables, you first need to choose one level of your k-level variable as a reference. So you just think about what level of the variable you want to serve as a comparison group, essentially. And then you create k-1 dummy variables. In the context of our region example, region has 4 levels, so k in this example is equal to 4. And therefore, we're going to create 3 dummy variables that we can then use in our linear regression models to get a better understanding of what's happening to blood pressure across different regions. And in this example, we're going to use Northeast as our reference. So to create dummy variables, you have to do this within a data step. Here's an example of a data step. I'm creating a new output data set called work.master3, starting from an input data set, work.master2. And then I have a series of if-then statements with some do groups to create the dummy variables. This is one approach to creating these kinds of dummy variables. There are many other ways to do it in SAS, so you may see other forms of it, but this is one example that would work. So just to talk through it quickly, I'm saying if the variable region is equal to 1, then do. And here's where I create my 3 new dummy variables for the first time. So when region equals 1 over here, this corresponds to people in the Northeast. And we could look to the code book to know what values of the original region variable actually mean. And these are the individuals in the Northeast. And in those situations, we're going to set all of our dummy variables equal to 0. So they should all take on values of 0, and that simply means that no, this observation is not in the Midwest, not in the South, not in the West. Okay? So you'll have 3 new variables at the end of all of this, Midwest, South, and West, and for all observations where region equals 1, those variables are going to take on a value of 0. And you can then end that do group with an end statement and a semicolon. Then we move on to the next line where we set up values of our dummy variables in situations where region equals 2. Now, the original variable, region, whenever it's set to 2, corresponds to individuals from the Midwest. So when we assign values to our dummy variables, we'll now say Midwest equals 1. In other words, these observations have membership in the Midwest group. And they again have values of 0 for South and West, because they're not from the South or the West, and so on and so forth. So when region equals 3, these are individuals from the South. Now Midwest will be equal to 0, South is equal to 1, and West is equal to 0. And then when region is equal to 4, that's when West is equal to 1 in this final if statement. So each participant or each observation in this data set can only have a value of 1 for one of these 3 dummy variables. And again, we've now created with this data step 3 new variables. So the new output data set, master 3, is going to still have the original region variable, but also a variable Midwest, South, and West. We can take a look at that now. Within the context of SAS. So here are some ANOVAs if you wanted to look more carefully at mean blood pressure across region. These are the ANOVAs I used to generate the graph that we talked about in the slides a moment ago. And here's the data step where I'm creating some dummy variables. And I'm just giving 2 different examples. They're both very similar. The main difference is in the reference. So in this first example, Northeast is the reference. It's identical to what we talked through in the slides. And in the second example, I determined that South would be the reference. I'll let you look through that a little bit more carefully if you want to understand it a bit better. But again, the main difference between these 2 blocks of code are that I'm creating 2 different sets of dummy variables. In one situation, Northeast is the reference up here, and in this second example, South is the reference. And now we could check those variables really quickly. So I'll just check the first set of variables that we made, and I'm going to use proc to cross-tabulate region with each of the dummy variables. I'm going to use the list option so that it's a bit more readable. And all I'm doing in this proc is trying to make sure that when individuals have a value of 1 for region, that they have values of 0 for Midwest, South, and West. When they have a value of 2 for region, then Midwest should have a value of 1, and South and West should have values of 0, etc., just to be sure that there was no error in my coding in the data step. I'll highlight that and submit it, and here are the results. So here is the region Midwest cross-tabulation, and as you can see, when region equals 1, Midwest takes on a value of 0. When region equals 2, Midwest takes on a value of 1, as it should, because region equal to 2 corresponds to the Midwest. And then when region is 3 or 4, Midwest takes on values of 0. In a similar fashion, South takes on values of 0 for all values of region except for 3, because region equal 3 corresponds to people from the South. And you can see the same thing when we cross-tabulate region versus West. So region equal to 4 corresponds to people from the West, and therefore these are the observations that should have values of 1 from West. Everything looks okay there. And now you can go back to your linear regression, and you simply need to model all 3 of the independent variables that you created, all 3 of these new dummy variables, as independent variables in your model statement. You can do that. We'll highlight and submit. And here's the output. And the interpretation now of each of these dummy variables should be pretty straightforward. Since each variable is 0, 1, we know that the regression coefficient corresponds to the change in mean systolic blood pressure for every 1 unit increase in the independent variable, or in other words, when you go from not being in that region to being in that region, those two comparisons. And since we're modeling all three of these variables together, the implicit reference group is going to be the northeast. Okay? So that's how the regression coefficients are interpreted in the context of dummy coding. And now we can go through each parameter estimate and interpret them a bit more. So for the Midwest parameter estimate, this says that mean systolic blood pressure is 0.84 millimeters of mercury lower among people in the Midwest versus people in the Northeast. Mean systolic blood pressure is 4 millimeters of mercury higher among individuals in the South in reference to individuals in the Northeast. And mean systolic blood pressure is about 0.32 points lower among individuals in the West as compared to individuals in the Northeast. Okay. So again, all of these parameter estimates for the three dummy variables are talking about the difference in mean systolic blood pressure in the region specified in reference to the Northeast. And why the Northeast? Because we chose the Northeast as our implicit reference group when we coded the variable originally. So we won't go into the detailed mechanics of how Northeast becomes the reference group, but you can think about that in a little bit more detail in terms of how reference coding works. I also want to demonstrate that and emphasize that when you create dummy variables, you need to include all of the dummy variables in the model statement. Otherwise, the interpretation of the regression coefficient will be changed. Let's look at this example where we just have Midwest modeled alone in the model statement. Now you see you have a parameter estimate of -2. Since you've excluded the South and the West dummy variables, the model now is going to tell you the mean systolic blood pressure in the Midwest as compared to everyone else, everyone not in the Midwest. So now the reference group is going to include people from the Northeast, the West, and the South. So here we see that mean systolic blood pressure is approximately 2 points lower in people in the Midwest versus people from the three other regions combined. And this parameter estimate is different, -2.3 and highly statistically significant, than what we saw when we included all three dummy variables in the model. So I'll just jump back up one page in the output, and here was the parameter estimate for Midwest when all three are included in the model. There it's -0.8 and not statistically significant. So it really makes a difference how you set up the model in many situations. And again, the reason we're seeing these differences is because of what the implicit reference group is in the two different models. Here the reference group is individuals from the Northeast, and in the second example where we only include one dummy variable, the reference group is going to be individuals who are in the South, West, or Northeast. And you could try similar examples using other regions as the lone independent variable. So here let's take a look at regression using the alternate dummy variables we created, where in those examples South is the reference. So we chose South as the reference in this example because South seemed to be the only group that stood out based on our preliminary analysis, for example using the proc ANOVA or a basic proc means above. We saw that mean systolic blood pressure seemed to be higher in the South, but pretty much equal in the other groups. So let's look at the results if we use South as the reference and see how blood pressures vary in the other three regions relative to the South. So now we have three regression coefficients for the Midwest 2 variable, the Northeast 2 variable, and the West 2 variable. And again, the interpretation of these regression coefficients is simply the change in mean systolic blood pressure when you go from not being in the Midwest to being in the Midwest. And not being in the Midwest in this particular regression means that you're from the South, because we're modeling all three dummy variables together. So we have a reference coding. And to say this another way, mean systolic blood pressure among individuals in the Midwest is 5 points lower than individuals in the South. And that's highly statistically significant. And there's similar interpretations for the Northeast in the West. So generally speaking, for all three of these regions relative to the South, systolic blood pressures are about 5 points lower. And those are all statistically significant, unadjusted for other variables in this data set. So now, building on that, I want to introduce you to proc GLM, which the GLM is short for generalized linear models. GLM has a number of very nice functions and statements and options, some of which are completely redundant with proc reg and some of which are unique to proc GLM. So it's nice to be aware of both of these linear regression procedures within SAS. The reason I want to talk about proc GLM is because it has a couple of nice features that are very helpful, and they're features that proc reg does not have. The first, building on our examples of dummy coding, the first feature that proc GLM has is the ability to use a class statement and to parameterize your categorical variables in a way that will give you the results that are effectively identical to dummy variables in reference coding. So in other words, you can model categorical variables very quickly and easily in SAS, and you can get results from effectively reference coding without having to create dummy variables. So let's consider this syntax, and then we'll go into SAS and give it a try. So I'm starting here with a proc format, where I'm creating some alternate region formats that we had not created previously. And the reason I'm doing this, as you'll see, is to control what my reference group will be in the GLM regressions. So for the moment, we won't go into detail about this. It's just a basic proc format, which you're familiar with, and the exact naming convention will become more evident soon. And the proc GLM syntax is listed below. So again, it's a procedure. It starts with a proc, specify GLM in your data set. I want to apply the region 2F format to the region variable. And I'm going to use a class statement here. And in the class statement, I will put various classification variables, or in other words, categorical variables, for which I want SAS to use dummy coding in the background. And then in the model statement, this is very similar to proc reg. You simply have your dependent variable set equal to your independent variable, or variables if we wanted to add more than just region to the model statement. And as an option to the model statement after this /, I'm using the solution option, which simply tells SAS to print the parameter estimates to the output window. I'm also including a mean statement and an LS mean statement. So what these additional statements do is explained in more detail on the next slide. Very briefly, the mean statement by default will give you sample sizes across levels of any class variables, and it will also give you the mean value of the outcome variable across levels of a classification variable. So any variable you have in the mean statement also has to appear in the class statement. And similarly, the LS means gives you the least squared means. And effectively, these are adjusted results, or adjusted mean values of the outcome variable across levels of any classification variables specified in the LS means statement. So in this particular setting, since we're not adjusting for anything, or in other words, region is the only independent variable, the results we get for mean systolic blood pressure from the mean statement and the LS mean statement will be similar. But if we were to add adjustments to this model in the model statement, and there were substantial confounding, for example, in the data, then the means generated from LS means would be adjusted for those other variables in the model statement. And they would differ from what you saw for the results of the mean statement. So let's go into SAS and give this a try. So here's the proc format I'm running to create some new format definitions that I want to apply to region. Let's put that. And here again is the GLM. It's a proc GLM. Here's where I apply my format. Region 2F created above to the variable region. I'm specifying region in the class statement because I want to view region as a classification variable, and in effect I want SAS to provide results that are going to be similar to the reference coding we saw from proc reg. A model statement that we've seen before, dependent variable equals independent variable, and in this particular procedure I'm going to include a mean statement also, so we can just look at the actual mean values of systolic blood pressure across levels of region. So here's the beginning of the output. You get some descriptive information about the regression. In GLM provides some ANOVA results. If you're interested in those, these are provided by the default. I'm going to skip down here and just talk about the actual regression coefficients for the region variable when we're using proc GLM and a class statement to model region. So effectively what's happening here is SAS in the background is creating a set of dummy or indicator variables for the region variable because we included it in the class statement. And it's choosing some reference level and then giving you parameter estimates that tell you about the relationship between any particular region and the reference region in relationship to systolic blood pressure levels. For example, in the West, the regression coefficient is negative 4.8, which means that in the West, relative to the South, which is the reference here, indicated by zeros, with no regression coefficient, in the West, mean blood pressures are about 4 to 5 points lower than they are in the South. In the Midwest, the mean systolic blood pressure is about 5 points lower than it is in the South. And in the Northeast, mean systolic blood pressure is 4.5 points lower as compared to the South. So these results, including the intercept term, are going to be identical to what we saw in proc reg when we modeled the dummy variables Northeast 2, Midwest 2, and West 2. If you wanted to go back and rerun that and compare, you'll see that they're the same. And in proc GLM you also have standard errors, t-values, and p-values corresponding to each of the regression coefficients. Now by default, the reference level of the categorical variable is chosen by SAS to be the highest letter that the format starts with. And whenever you use format, SAS will base the ordering based on those formats, and since I named the formats starting with WXYZ, I did that simply to control which level of region would be the reference, and in this example, because I started the region South with a Z, that is the reference. Here is the output produced by the means statement. So you get 4 levels of region, the sample size in each, the actual mean systolic blood pressure, and the standard deviation. So just to give you a comparison of what would happen if we did not include a region, or excuse me, include a class statement, I'm just going to comment out the class statement. And I'll also comment out the format statement, since the only reason we had that there was to determine what group or what level of region the reference would be. And if we rerun this, you see we're back to our basic linear regression model, where the model assumes region is a variable with values 1, 2, 3, 4, and there's a strict linear relationship between these arbitrary levels of region and the outcome systolic blood pressure. Okay? So again, these are the results if you do not specify to SAS that you want to define region as a classification variable and insert it into the class statement. Now you'll also notice in this example, if we go to the log file, I had not silenced the mean statement, and that gave us an error. SAS still ran the model statement and gave us results, but of course we didn't get mean values of systolic blood pressure across levels of region because region was not specified in the class statement. I just want to make it clear that the reason the class statement was not specified in this model is because I silenced it by putting an asterisk in front. As we talked about previously, any syntax enclosed in between an asterisk and a semicolon, SAS will effectively ignore. Now if you wanted to run an adjusted regression, let's go back to the region systolic blood pressure example, but now adjust for age. We're worried that maybe participants in various regions might be older than in other. So for example, people move to the south and the west for retirement, so on average age is going to be older in the south, and that could be driving higher blood pressures potentially. So this regression model will adjust for age, and again we have region specified in the class statement, so SAS will effectively give us parameter estimates that can be interpreted as if there was reference coding. I'm also going to include a mean statement, and we'll see the results from that, and then an LS mean statement where I've included options OM, which stands for observed marginals. This option simply tells SAS that the categories are not balanced. In other words, there are different sample sizes in each level of region, and that should be accounted for when calculating the means and standard errors. I'm requesting a matrix of p-values that will give us p-values corresponding to any two-way comparison between various regions, and I'm also asking for standard errors in the LS means output. Again, the beginning of the output, we have some basic information. I'll jump down to the regression coefficients. And here are the regression coefficients for the West, Midwest, and Northeast relative to the South. They're slightly attenuated. As you recall from the previous examples, we had regression coefficients of about -4 to -5, and now they've been attenuated to approximately -3 to -4 after we adjust for age. But nevertheless, there's still about a 3 to 4 point difference between each region and the reference region of the South, and on average the blood pressures are lower in Midwest, West, and Northeast as compared to the South, and those differences are statistically significant, which you can see by interpreting the respective p-values for each regression coefficient. And in this model you also see that after adjusting for region, age is positively related to systolic blood pressure. Here are the results that are generated from the mean statement. So again, we get sample sizes in each region. Here are the mean systolic blood pressures, unadjusted for anything else, across region. And since age is a continuous variable in the model, SAS will also give us the mean values of age. And then these are the results from the LS mean statement. So these give us the mean systolic blood pressure levels after adjustment for age. You can see how they vary, and they're slightly different than what you see up above in the mean statement in the previous page of output, because these are not adjusted for age. Going back down to the LS means, in addition to the actual adjusted means, you also see standard errors. And these t-values are simply t-values that are one sample t-values asking whether or not this value of 131 is different than 0, etc., etc., for each of the respective mean blood pressures in each region. And these standard errors, again, are generated because we used the STDERR option in the LS mean statement. So this option here. And then finally, this pdiff option is producing this matrix of p-values. The way you interpret this is you simply look at the LS mean number corresponding to different levels of your categorical variable. So imagine we want to look at a comparison between the Midwest and the West. That would be a comparison of LS mean number 2 versus 1. So we can come down to the matrix and we look at level 2, and we come down to the first row corresponding to level 1, and that p-value is 0.3. There's no statistically significant difference between mean blood pressures in the West and the Midwest. Alternatively, if we wanted to compare, say, the Midwest, LS mean number 2, versus the South, LS mean number 4, that comparison would be given here. So here's 2, and we just go down and compare it to 4, because this is the row corresponding to 4, and the p-value is less than 0.0001. Here's an example where I'm using the original region format. So instead of region 2F, I'm using region F, where the formats were set up slightly differently. And again, this is just to demonstrate how the reference group is chosen when you're using formats for variables specified in a class statement within proc GLM. As we said before, it will look alphabetically and take the highest letter, and since W is the highest letter, West becomes the format or the reference in this particular example. So again, this is because we used the original region format, and just as a reminder, that original region format was defined way up at the beginning of this code when we started. So there's the example. Now let's think about, real quick, the overall question of BMI and systolic blood pressure again, and build in some tools and procedures that we've used in previous lessons to move from a linear regression that would be modeling just the BMI continuous variable by itself, but instead modeling some categorical BMI variable so that you could look at the association from different perspectives and under different assumptions. Now again, here's a general regression model that would just have BMI as the independent variable and systolic blood pressure as the dependent variable. And we can run that model, and as we saw earlier on in this lesson, the relationship here, the parameter estimate, shows that for every 1 unit increase in BMI, there's a 1.5 unit increase in systolic blood pressure. And we could move on and categorize BMI into 5 levels. For example, if we wanted to look at a 5-level classification variable and see what the relationship was between different levels of BMI grouped categorically and the outcome systolic blood pressure. But one way to do it would be to go into a data step and use if-then statements. But if we don't have any real preference for the definition of the categories for BMI, and we just want roughly balanced groups, we could use proc rank, as we've talked about previously. So in this proc rank, I want to take the input dataset master 2. I want to create an output dataset master 3. I'm going to use 5 levels of groups. And I want to take the variable BMI, which exists in the input dataset master 2, and create a new variable called BMI Q5. which will rank the original BMI variable into 5 levels, because we specified groups equals 5, and it will output this new variable to the new output dataset master 3. Then I can move forward and run a regression on master 3, specifying BMI Q5 in the class statement, and then also in the model statement, and adjusting for age. And again, I'm using a means and an LS mean statement so I can get additional information about systolic blood pressure and how it varies across levels of the BMI Q5 variable. So I'll highlight all that, submit it at once. I'll page down to the parameter estimates. So in this example, BMI Q5 has numeric values 0, 1, 2, 3, 4 corresponding to 5 ordered levels of the BMI variable. We generated this in proc rank just a moment ago. And you'll notice that we didn't apply any formats to this particular variable. We're just letting the actual raw numeric values be displayed. And when you do that, SAS will pick the highest level of that variable as the reference. So 4 is picked as the reference by default, and your parameter estimates then can be interpreted in the usual way. So we see that in reference to the highest category, or the 5th quintile of BMI, individuals in the 1st quintile of BMI have mean systolic blood pressures that are 15.9 points lower on average. Corresponds to the regression coefficient of negative 15.9. Individuals in the 2nd quintile of BMI have mean systolic blood pressures that are 13 millimeters of mercury lower as compared to those in the 4th quintile of, or excuse me, the 5th quintile of BMI, and so on and so forth. And then you have t-values and p-values corresponding to each of those regression coefficients, as is usual. And we also included age in this model, so we get the regression coefficient summarizing the relationship between age and BMI, and that means that in this particular model, this parameter estimate for age is adjusted for BMI category, and the results for BMI category are also adjusted for age. Again, the mean statement here is providing results, some descriptive results across levels of the BMI Q5 variable. So here you have your sample sizes in each of the 5 groups, unadjusted mean systolic blood pressures, and unadjusted ages. And the LS means statement gives us the adjusted mean levels of the dependent variable in the model. So after adjustment for age, mean systolic blood pressure levels are 126, 129, 132, 134, and 142. Here are the corresponding standard errors, and if you wanted to do any pairwise comparisons of these, any one level of BMI with another level, you would get p-values from this matrix. And you can see here very quickly, just from scanning through it, every pairwise comparison of these 5 levels of BMI is statistically significant. And then finally, I'll just show you proc plot since we're in the editor file. Proc plot is a very quick, simple, useful tool that can help you generate scatter plots, which are often helpful when you're first beginning to look at and describe the data, maybe make some early judgments about the degree to which there could be linearity or not between your exposure and your outcome variable. So this is a procedure. We start with proc, specify the plot procedure and the data set we want, and one of its most basic and useful forms in proc plot, you simply specify the plot, the plot statement, and then you want to give your y variable combined with your x variable by an asterisk. So SBP times BMI, and a run and a quit statement. And this gives you a very basic scatter plot. With really large data sets, the scatter plots can sometimes be not terribly informative in SAS because SAS does not have a good way in its default mode to show you when there are a lot of essentially identical observations. So for example, to interpret this scatter plot, each letter corresponds to the number of times an occurrence of these data pairings happened in the data. So for example here, there was one situation where an individual observation in the data set had a BMI of approximately 41 and a systolic blood pressure of approximately 270. Okay. Alternatively, you see there's a B here. That means there were two individuals who had a BMI in this situation of maybe about 18 and a systolic blood pressure of about 80. And so on and so forth up to Z, and beyond Z the observations just get hidden. So this is telling you that 5,035 observations are effectively hidden because SAS had no way to actually provide information about how they were plotted in this scatter plot. But it still gives a basic view of how the relationship looks, whether or not there is clearly no relationship, or there could be some linear component, or if there are odd outliers in the data. And if you want to change the symbols from the letters to some other symbol, you can simply add an equal sign after you specify the cross-tabulation of the two variables you want to plot, and then after the equal sign, specify the symbol you like within quotes. I'll use a plus sign here. So now we get a scatter plot where each data point is plotted as a plus, and notice here that many more observations are hidden because you can only plot the plus symbol one time. In other words, you can't represent points for which multiple observations had similar data patterns. These are just some descriptors of what various statements within proc GLM will do and various options. We've talked those through. This is a reminder that of how reference coding for variables in a class statement will be handled, whether you use a format or if you don't use a format. And if you want to explore this further to come up with different orderings and control the reference groups in more detail using other methods, you could look at proc GLM user guide and particularly pay attention to the order equal option in the proc GLM statement. So that can help control the order in which variables come into the regression, and therefore what level of a categorical variable might be specified as the reference. But generally speaking, the easiest thing to do is simply use a format, and before you run the regression, define that format using rules that will set the reference group appropriately. In other words, make sure your reference group has a format that begins with the highest letter out of all values specified within the format. This is just an overview of the proc plot that we discussed and went over in the SAS editor file just a moment ago. And some additional descriptives on proc plot. I included this table to help give you a sense and overview again of how to think about the form of your data, what analysis might be appropriate, and what SAS procedures you could use to do those analyses. So for example, if you have a binary exposure variable with values of 1 and 0, for example, and also a binary outcome variable with values of 1 and 0, you might consider using some contingency tables. And in SAS, we've talked about proc freq and various categorical analyses that can be performed within proc freq given that data structure. Proc tabulate is another option that we have not discussed within this course, but you could look into that and see whether or not it fits your analytical needs. Alternatively, you may have a categorical exposure variable with more than 2 levels. So we talked about region as one example, and an outcome variable that's continuous, such as systolic blood pressure. And in that context, you could use ANOVA or linear regression and these procedures within SAS will run ANOVAs and linear regressions. So in summary, we've talked about proc reg and proc GLM, so you should understand how to set those procedures up for various linear regressions you might want to run. You should know how to interpret the intercept and regression coefficients from linear regression output in SAS. You should know how to create indicator variables if you should ever need to do so. Those are created again within a data step. You should also understand how to use a class statement within proc GLM so that you could model a categorical variable using a reference coding parameterization that would relax the strict linearity assumptions inherent in linear regression. And we talked briefly about scatter plots using proc plot.